My final example here that I'm going to use L'Hopital's rule with gives us another indeterminate form. So if I were to plug in infinity to this, so just inside here, I'd end up with infinity over infinity, which by itself is an indeterminate form, but I still have this exponent too. So if I take 1 over infinity, that is basically moving towards 0. So I kind of have a lot of indeterminate forms going on here, but it is not the basic indeterminate form, which means I cannot use L'Hopital's rule yet. So I'm going to use logarithms to actually go through and solve this. And what I mean by that is I'm going to do ln of this whole thing. So what that allows to happen is allows this exponent to drop clear out here in front. So I'd have 1 over x ln of x squared plus 1 over x plus 2. So I still don't have the infinity over infinity because I have 1 over infinity and then ln of infinity over infinity. And so this will be kind of a little trickier thing. And you do have to keep in mind that since you do introduced an ln, there is something that we have to do to cancel that at the end. If you recall, to cancel an ln, we use an e. So we will have an e come into our final answer here. So what I would do from this point so I can get that indeterminate form that I'm looking for is I would do ln of x squared plus 1 over x plus 2. And then I would take it times this 1 over x. So imagine that this is over 1. So all of this is over x. So I have all kinds of infinities over infinity here, which does make it a mess on a derivative, but it's going to work because it's now L'Hopital's situation. It's that indeterminate form, and I can mess with it. So once again, I'm going to derive the top, and this does get a lot messier, but I'm going to shorten this out a little bit. By using my properties that I know. So x squared plus 1 minus ln of x plus 2 all over x. So I still have like infinity minus infinity over infinity. It is kind of a mess, but I do have it. So I can still do L'Hopital's rule with this. I basically have infinities over infinities. So when I use L'Hopital's rule, I'm going to do the limit as x goes to infinity just so I don't lose that. And in fact, I'm going to go ahead and put this e on here because I know I'm going to do e when I'm done. And if I don't do that, I will forget about it. So now let's derive this. So the derivative of this part right here is 1 over, here, I'll even back up so you can see it, 1 over x squared plus 1 times the derivative of what's inside, which would be 2x. Okay, minus 1 over x plus 2, the derivative of that would be just 1, and then all over the derivative of the bottom would just be 1. So if I were to simplify this a little bit, I'm going to have the limit as x goes to infinity of 2x over x squared plus 1 minus 1 over x plus 2. Okay, so now I have two fractions being subtracted. I could go ahead and try infinity, but right here I can see I have infinity over infinity and then 1 over infinity. That gets kind of messy. So let's get common denominators on this so that I can make it a fraction, one function over another, and see if L'Hopital's rule does apply again. So this is getting kind of messy and long, but these problems do have that kind of fun feature to it. So I have 2x, and then to get common denominators, so notice with the derivative, the ln did go away, but the rest of it is still there. So right, for this part right here, I'm going to have a 2x squared plus 4x, then minus x squared minus 1. So I will have the limit as x goes to infinity, e to the. I'll end up with an x squared plus 4x minus 1 on top. Now on the bottom, it might make, you can leave it separate or you can FOIL it all out. It's up to you. I'm going to go ahead and FOIL it out because If I have to do L'Hopital's rule again, it is easier to do a derivative of just a quadratic or cubic in this case versus trying to do a product rule, which you could do either way. It really doesn't make a difference. But I have x cubed plus 2x squared plus x plus 2. All right, so now if I were to plug in infinities, yes, I have infinities over infinities, so I can use L'Hopital's rule again. Now I am going to get another sheet of paper in which to do that on. Okay, so I'm going to have the limit as x goes to infinity, and then I'm going to derive that function up there. So I'm going to have 2x plus 4 over 3x squared plus 4x plus 1. Well, if I plug in infinities again, I still have infinity over infinity. So let's try this again. E to the limit as x goes to infinity. So on top now I'll have 2, and then I'll have 6x plus 4. So if I plug in infinity this time, the top is 2, so I already know I don't have that indeterminate form. But I'm going to have 6 times infinity plus 4. Well, anything times infinity is infinity, so right here, this gives me 2 over infinity. And when we talked about this early on when we talked about limits, we said 2 over a very large number is basically approaching 0. But 0 is not your final answer because recall back here we have the e to the. So we e power to the 0, and e to the 0 is 1. So our total final answer of this limit is 1. So a lot of work for such a simple answer.